All right, so we're recording and welcome audience. So today Ian and I are going to do like a quick sort of like brain session looking at a very interesting YouTube video on mathematics and relationships. And I'll just quickly describe how I bumped into this. So basically I've just started my journey into romance for the very first time. And I thought the best way to approach this is maybe by doing some literature search, maybe by looking at what other people have explored, and of course doing informational interviews too. And so as I was on YouTube, like I was just like, what's out there? I saw this talk, and I'll start my PowerPoint. Maybe I'll share screen. Um, and I found this really interesting talk by John Gottman, and it was called The Science of Love. And he also has this mathematical approach to what he does. And so part of what he does, I saw these interesting phase plots, which look just like the data that I have. And that's what got me interested in it. But I guess before we go on this, let's just do our quick introductions. So I'm Vivek Anand, and like my work that I do is on spatial disorientation. I strap people into a machine, and then I use phase plots to sort of look at how they stabilize themselves. And then Ian, maybe you can give a quick introduction to yourself.
Yeah, I guess I'm also a student at Brandeis. I'm a graduate student. I'm actually going to defend my thesis on my PhD work this next Monday, so
Yeah,
wrapping it up. And yeah, I guess
congrats on that, by the way, too. It's just
yeah,
an amazing accomplishment.
thanks. I'm excited to do new things, and it's been a fun journey thus far.
Mhm.
And yeah, I've been in the physics department actually, working with Seth Frayden, and I've been studying coupled chemical oscillators, which I know sounds like a sort of weird thing, but basically just think of very small things that change color periodically. So they kind of flash, and they couple to one another. So if you have two of them next to one another, they'll try to flash at the same time or at opposite times one another. I guess I met Vivek through him trying to create all these sort of collaborative meetings at Brandeis, and he also studies oscillations of sort of people trying to do something, and yeah, I guess we've at various times it seemed like there might be some connections between the sort of oscillations I see in these chemical reactors and things in neuroscience, including what Vivek has observed.
Yeah, and it's
Yeah, I
been really.
also I forget what we were talking about, but um, yeah, Vivek brought up this YouTube video, and very fascinating. I mean, and also it's not just kind of out of nowhere. The author of it, John Gottman, collaborated with a really well-respected mathematical biologist named James Murray, who is super well-respected and was involved in this project. So the fact that it wasn't just some random TED talk about love and somebody claiming to have solutions was sort of tantalizing to me. And yeah, so I mean, you want to
Yeah,
get
thanks.
into it?
So for people to just get like a quick preview, so this is the TED Talk. You can the science of love. Oh wait, let me screen share. Screen share. Okay, so this is the TED Talk. If you search for it, maybe I'll start this presentation. Um, and it's by John Gottman, The Science of Love. And I tried to look for the underlying papers, but I had limitation in time, so I didn't find all of the actual research papers. So this like informal conversation will just be based off of this TED Talk, and I have screenshots. And just to sort of bring you up to speed, what he did and what his group did is they brought in different couples, and first the couple comes in and they do like a survey just to get a sense of like, how is this couple, are they happy, sad, whatever. Um, and then they'd interview the couple and get some like, information from that. One of the novel things I thought that they did, I guess other people do it as well, is they measured actual physiological measures. So like their heartbeat and other metrics as the people are actually conversing with one another, sometimes having very difficult discussions and you're looking at what their heartbeat is doing. So that was kind of cool. And then I guess like they took videos of these people and scored their emotions second by second. And they even had, I guess, like the partners like watching the other partner and then rating sort of what their emotion and their perception was.
Yeah, I
And
guess
so,
from watching the video, I sort of hypothesized that what happened is they filmed the whole thing and then after the fact they would do the rating thing.
That sounds
But
about
I
right.
don't know. It's not clear to me.
It's not, yeah, you know, like there's only so much they can do in the video. I mean, these days people would use machine learning to extract like emotions and things like that. But most likely, I think what you're saying is correct, that they recorded it and then afterwards looked at it. And then either way, they got this time course data, which over time you had like behavior, perception, physiology, other measures, and you have both like partner one, partner two, and you could see what they're doing. So this is already kind of interesting that, you know, partner one may be spiking up behaviorally, and so is partner two. Maybe there'll be something that's opposite. This is already cool because I work with time course data. I work with human balancing, and so you get something that's very similar to this. Ian, do you work with time course data, or do you go directly to like phase plots and stuff?
Yeah, yeah. So the flashing colors of our reactors changing in time forms, in some ways dissimilar, in some ways similar plots to these.
Mm.
So a similarity is that, we have multiple different colored trajectories evolving together. There's one different color for each of the different reactors that we're studying, tracking whether each individual reactor is sort of dark or bright.
Mm.
And that it's similar in that, we track those quantities over time. Though obviously, instead of something like behavior, which I don't quite know what that means. I mean, we track something that's more like a millimolar of some chemical
Mm.
that's creating a color. But the final similarity that I would say is the fact that there can be states in which the different time series overlap on one another, meaning they're all the same value as one another, which is known as synchrony. And you're seeing here in the behavior, the husband or the wife or partner one, partner two, they're synchronized. So I find that quite interesting. It's an odd similarity I wasn't really expecting.
It is cool, yeah. And for you, you have like, yeah, you have chemical oscillators that can be synchronous or asynchronous or whatever. And with mine, I just have one oscillator, but I can look at things like, well, what are the position and velocity doing together, and what the joystick is doing, and is the joystick and position velocity synchronous or not? So there are some cool similarities in what we look at. So he takes this time course data and he makes what he calls a phase plot. And this is exactly the plots that I make for my data. And I'll show this my data at the end. This is what like really grabbed my attention. And I was just like, whoa, this is cool because it's so similar to what I'm doing. So this is a graph, and on the x-axis is what they call this is a husband-wife pair, the husband score. And if you're on the right, that's like positive. So the husband's feeling really positive. If you go to the left on the x-axis, the husband's feeling very negative. And you can kind of see this husband's face showing that. And the y-axis is the wife's score. So if you're up on the top, she's positive. So in this first quadrant, both are happy, both are positive. And if you go to the third quadrant over here, then both are sad. And then in the sort of like the second and fourth quadrants, you'll have one happy, one sad. So this is the phase space that he looks at. And what he does, and I think we have a video that I can show from the TED Talk too, but what he does is he maps how during a conversation do the husband and wife interact with one another. And maybe I'll show that video first. So that was 2052.
So you wrote that down. I had no recollection.
Yeah, so right here, and I think he's talking, and it's going to soon start, and you can see how these people's trajectories is going.
So there's the first data point right there, the little blue X.
And you can see it's jumping around. And so that's like an example, I guess, of like a phase plot evolution. And then Ian, you had a few points on this that you thought were interesting.
Yeah, I mean, I don't know. I'm always interested by the real data when people are talking. But yeah, I guess I found it very odd that, in the beginning of the talk, he shows these time series in which, I guess it's each of the partners' behavior, which I guess I should just quickly say, I'll use the gendered language of wife and husband. just because all the plots are in terms of that. I think there's probably a better term, or it's more neutral, but suffice to say, right, in these plots, all of these quantities are varying nice and smoothly and gradually. So that would make me expect that, if I take the husband's, value and the wife's value, and I plot them versus time, there shouldn't be these big jumps. It should be maybe a loop or a slow, I call trajectory path through this phase space. Yeah, so right, in this first plot, the first point that they show, I would assume would be time equals 0, so the leftmost point on those plots that we showed you, and I would expect at the next recorded time, some very small distance away, you'd see their scores having changed just a little bit in some direction. So I don't know. I mean, there are a bunch of reasons why they might have done this. I mean, maybe Gottman wanted to show this very quickly, right? A TED Talk's pretty timed. So maybe he just showed the most interesting events. But it is odd because, right, they go from neutral, right? Their scores are near 0 in the beginning. And just immediately they shoot up to the top left, which means, the wife is happy, but the husband is not. So I don't know, maybe she told some off-color joke right in the beginning or something. But it's just bizarre to me how fast it shoots up. And then then they're both unhappy, I guess, for a little bit. And then at the end of the video, they're kind of back at neutral, maybe. Like, right, they're not super far in any particular direction at the end.
It's true.
Which is interesting, right? Because all the stuff he talks about later in the video is not about the partners staying neutral. So, I don't know, there are many ways in which this video doesn't super support the, I guess, if you showed that plot of the conceptual picture of them moving to one of these two attractors, right?
Oh, I'm going to get to that. Yeah, just to address.
Ahead in time.
Oh, no, this is good. These are my phase plots. If you look at the left graph here, you do have these loops as time is going by. And again, my system is a lot simpler. It's just one oscillation that's happening as a person is trying to balance themselves. But this is typically maybe what you would see in a trajectory, and my time course data kind of looks like what his does. So I mean, obviously he has multiple metrics here. We haven't read his papers, so we don't exactly know what they're doing. But it is interesting in human dynamics how much maybe emotion can supposedly maybe jump around like crazy. And it was just something interesting to see. Now, to address what Ian is saying, so like what he next shows in his video, this is more like maybe like a simulation or like an example, is that in this phase space, where again, to orient you in the first quadrant, this is where husband and wife are both positive. What he's saying here is that no matter, there are attractor points, and Ian, correct me if I'm wrong, are sort of these points where no matter what your initial condition is, the system sort of goes there. It's sort of like a pull in a way that you can start here, you'll end up here, you can start here, you'll end up here. Is that a okay definition?
Yeah, I think that's a perfectly good definition. I'd say for a given system, the attractor is just a state that many times you run the experiment, the system kind of converges to. So, for example, if I have a little fruit bowl, or I don't know, even a coffee mug, and I take some random thing on my desk and put it in, the attractor will be that thing just being stuck at the bottom. So in general, attractors are sort of a valley in some landscape.
Exactly. And so here what he's saying is that if you have a positive attractor state in the first quadrant, that's really good, because no matter where you start from, you'll always sort of converge to this place where both husband and wife are happy. Even if you're somewhere negative initially, you can come over here. Whereas a more negative couple may have an attractor point in this third quadrant, where no matter where they start from, they end up always becoming negative and angry at each other. So his point is that maybe these attractor states exist, and he is using data, then he's able to construct diagrams like this, kind of showing that. So this is a stable, unhappy marriage. So the attractor point is in the third quadrant where both are negative. And again, you could kind of look at these flow charts, like if you start off in the you're both very, very happy, I guess according to this model, you'll eventually flow into both being kind of negative. Um, and then for a happy, stable marriage, you would have a point over here, and you'll, even if you're negative, you'll sort of end up in a positive place. Just an interesting way of showing the data. So Ian, you also had some points before I get into mine on like the math behind it, which I can bring us to.
Yeah, well, I guess, I mean, just one first comment is just about the plots you just showed,
You can
right?
bring it back
And
up.
maybe how you read them.
Yeah.
You go back to the, yeah, so I mean, the way that you're supposed to read these plots is,
This one or this one?
no, the one with the vectors on it. Yeah, so, I mean, the way you're supposed to read these plots, right, is it's to say, if I'm at any point in this phase space, it's called, and I put my arrow down, say, where Vivek has the arrow now, his mouse arrow, wherever that is, right, look at the gray arrow underneath it. That is predicting where the system's going to go. So, right, we can then trace these gray arrows. It's like following a path of breadcrumbs. And then, right, we see that those arrows all lead to the sun, which that's representing the attractor. And right, we can see no matter what direction we go on, all roads lead to Rome, apparently, where Rome is an unhappy marriage. In this case, apparently, for this couple. And so, but this is quite odd, right? Because the actual data that he showed was not this sort of monotonic path towards one state, but these wild oscillations where, you go from here where they're neutral to, wife happy, husband unhappy in like a blink of a second, and then they kind of jitter around. So I would hypothesize that this is to be understood in a very averaged sense. That this isn't saying that actual adults in conversations, the tone of the conversation smoothly changes in this way. I mean, at least in my experience, if you say even a slightly inappropriate thing, that can really skew things very rapidly. So I think the way that we look at this is there's a lot of randomness added on top of this. Anyhow, I am going to at some point look through the papers more carefully from this fellow to try to understand what exactly is going into these.
Yeah, and then for anyone watching the video, if you want to join, you're always welcome because, this is just an initial exploration. And then when we look at the papers, we'll have a better understanding of like what the methods were and what they did. And, I think probably a lot of those diagrams were just constructed from these math equations. So I mean, Ian, you had some thoughts on these math equations?
Yeah, so I mean, I think I can give a pretty brief, accessible explanation of these. So, right, the idea of math in general, and especially dynamical systems, is to, given knowing about the current state of a system, be able to make some helpful predictions about what they'll do in the future. So, for example, in my work, I work with these chemical reactors. We're often interested in predicting the types of patterns they'll form in the long run. So we ask, if I connect 3 oscillators together, what types of patterns will they form as opposed to 4? Is there some benefit to connecting 4 versus 3 if we have a particular pattern in mind? So, in doing so, we consider the current state of the system and what will happen next as a way to find what the attractors of the system are by running many simulations where we consider many initial conditions and finding where they converge to. So in this case, these equations aren't too complex. So we make the big assumption that there's some number for each of these people. In the case of the wife, it's indicated by W at time t. So, we could say that's at 12 o'clock. And that's indicating how happy she is. So if it's positive, she's happy. If it's negative, she's not. They're not, I should say. Likewise, with respect to the husband at, say, time t, which can be 12 o'clock, it's the same time for each of them in this model. this number h is indicating how happy or unhappy they are, and it's meant to be in the same sense as the wife. So positive good, negative bad. And then we're seeing that there's some function that determines ht plus 1. So t plus 1 isn't saying, it's just saying plus some more time. So probably 30 minutes, I don't know, 5 seconds. I don't know what their resolution is here, but this is just representing that there's sort of a next step in time. And then, we should notice that these are pretty similar for each of the two people, which makes sense. I mean, even though we've labeled these two people based on genders, people are ultimately pretty similar, regardless of gender, at least in my experience. So we should assume there's not too much of a difference. And so, they're saying that firstly, there's something that they've labeled a constant that's unique to each of the two partners. So in the case of the wife, it's denoted A. And what that means is that, let's say, so this is saying kind of, if all these other terms were 0 and A was 2, a positive number, this would say no matter what happens, the wife will always be happy at level 2, right? Because if WT plus 1 is equal to 2, there's no change. It's just the same. And likewise with the husband. So this raises the point that, in the absence of any input from the partner or history, we can say that the two partners are some level of baseline contentedness. So, for example, we could say maybe the wife is very happy. I mean, maybe she just got a new job, or she's just made a piece of art, has lots of fulfilling hobbies and friends, which is positive. You could then say maybe the husband is unhappy, maybe, I don't know, they have kidney stones, something bad. So B is just negative. So in the absence of anything that their wife does or their partner does, they're just unhappy. So that's already, you can see this is sort of a core ingredient. It's kind of the natural state of the person will influence their dynamics. So this is very simple. This is just saying constant. On the other hand, so now we're adding some past history. So here we're saying that there's going to be some dependence of your state in the next time based on your state now. So, and it's proportional, just linearly proportional, just to say it's not to the power 2 or anything weird like that. It's just saying R1 is multiplying this number. So to just provide an example, let's imagine, just for the sake of argument, that the wife is neutral. So A is just equal to 0. Well, then if R1 is positive, that means if the wife is currently happy, if R1 is 1, then R1 plus WT plus 1 is just equal to WT. So just stay the same. But if R1 is a large number, then, let's say wife is currently very happy. Then if this is 2, then in the next step, she'll be twice as happy. They'll be twice as happy. So that's kind of an interesting thing. So I would say this is representing how much people care about the past. Somebody who really lives in the moment, this is 0. So, and same for the husband. I mean, same argument holds. It's just R1 versus R2, indicating that they're slightly different, probably not super different. And then, then we get to this juicy part, which is made a lot more mysterious. And based on their talk, I really have no idea what this is, but there's this quote influence function that's just saying that your state in the next half an hour, say, is influenced by the current state of your partner, which is very interesting. This is saying just their current state. So we've been saying, your partner in this model could have done anything. I mean, maybe they crashed the car or something like that. But as long as it was above 30 minutes ago, it's not currently now, it doesn't matter. So that's already sort of an odd thing in this model, but anyhow, it's saying that the current state of your partner has some influence on you. So qualitatively, I mean, this is some nonlinear function that I don't know, so I can't say too much about it, but I can say that you could depend on, in different ways, qualitatively different ways. So for example, the wife or the husband, based on their partner, could be made happier if their partner's happier, or the opposite. I mean, I don't know what exact psychological arrangement would lead to this, but you could imagine a situation in which somebody is, say, very jealous, and if they see somebody very happy, they feel negative. So this is something complex, and I think this is encoding a lot of interesting relationships between the two. But I think that's my summary of the model. I think I've already talked more than I want to. But basically, the takeaway I would say is that people have some sort of intrinsic dynamic. People have some capacity for remembering the past. So people can be more instantaneous or more, I don't know what the word would be, but have longer memories. And then they care in varying ways and to varying degrees what their partner feels at that current moment.
And so, this is a little bit off topic, but now I'm fascinated because, I appreciate like the thorough introduction into the equations. The equations that you deal with for your chemical oscillators, obviously there's like, you've got chemicals diffusing and this and that, but at like the really bird's eye view of it, is it similar vibes? You have a constant, and then one oscillating system, one droplet is coupled to another, or do your equations have other terms in it that this doesn't have?
That's a very good question. So I would say that the first thing that's very different between them is the chemical reaction I study is not fully understood. It's very complicated. So it's known to be composed of 40 different chemicals reacting through 80 different reactions with one another. So even the most simplified models that we use, which are known in the literature to be on the verge of almost too simple, there are 4 variables per reactor. So we track 4 different chemicals. One of them is bromide. One of them is bromous acid. I think most of those won't mean much to people. But suffice to say, we have a lot more going on than just one variable. Mm. So here, a person is being represented by a single number, but in the chemical reactors I study, to get even remotely decent fits to data, you have to track multiple different chemical species. So, you could imagine if this model would be more like my models, if, for example, they tracked maybe the income of each of the partners, or how hungry each of the partners were at the time. Maybe it turns out if you've eaten a sandwich recently is an important determinant of relationship happiness.
It's interesting, because with all of these models, it's always a question of how much can you put into it. And in some ways, some of these constants and values absorb in like everything, and you get like a bulk feeling level. But then the question is that you have now a very simple model, but is it really representing the dynamics of a system? So yeah, it's a deep question. It is, and it's, I think, humbling and good to know that, like, like from my point of view, two chemicals oscillating is like way simpler than a human love like relationship. And yet, even with that, you've got like whatever 80 chemicals or whatever you said. I mean, it's interesting to think about how complex some of these things are, and
yeah,
how much we may lose from simplification, or how much we may gain. I don't know.
Yeah, I mean, right. At least in physics, the goal is always to create a model that's just complicated enough. You want it as simple as possible. And an interesting thing that I've observed from going to biophysics talks is that even though biology is always way more complicated than any of the chemical reactions that I work with, because sort of biology is based off of evolution, and things are so optimized and so specialized, sometimes pretty complex behaviors in biology are described by very simple rules. So to me, it's not obvious either way. I mean, I'm 100% sure that there are way more things going on inside an individual person than just one variable with respect to their partner. But I think, your perception of your happiness, which basically this is what this model is tracking, it, to some degree, is sort of a one-dimensional thing. I mean, I can definitely say I'm more happy some days and less happy others. So yeah, I don't know. I think I mean I really want to delve into the papers more,
Mhm.
and the person who helped develop this, James Murray, I really trust them in terms of their, because they've approached many very interesting problems very accurately.
Mhm.
Um, Again, balancing simplicity with sort of predictiveness and simplicity. So I don't know.
Yeah, I'm looking
I
forward
think
to. I
it's
mean,
simplifying, but just
this.
to continue on, I mean, I would say the other things that are similar between what I study and this model is that kind of there's an element. So right here we have a two-person model. In my systems, I study multiple different chemical reactors, which have a similar feature in that, right, people are pretty similar to one another. So the forms of these equations are the same. Similarly, I assume the forms of the equations of my different reactors are all the same, but these different terms or coefficients are slightly different between them. So there's some extent, and one of this paper that I've actually submitted for review, and hopefully we'll go through a physical review letters X. A big component of it is in fact small differences between these reactors can have a big impact. So, I mean, on the one hand, right, you can say, okay, people are very similar, but in a model like this, it might be possible to see that even small differences can cause important effects. And so, just to get a little bit more specific, then each of these actors, partners, they have a sort of a self term, and that's the sum of multiple terms. So here it's a sum of a constant and something related to your past behavior that has no dependence on what your neighbors are doing, what your partner is doing. So right in my reactors, there's certain chemistry going on inside the reactors, and that's pretty much just governed by some terms. I mean, they're not too different than this. They're like constants and linear terms and squared terms, some others, but that's pretty much it. Um, and then there's some coupling terms that mediate your relationship between, you know, those, in this case, they're governing how the emotional state of your partner affects your emotional state. In my models, it's showing how, if my neighbor is in chemical state A and I'm in chemical state B, how I'm affected by that. So there is a similarity in which you're saying at some level you can abstract something as being specific to one unit, and that there's something that's mediating coupling between these independent units.
Mhm.
Because, I mean, for example, one could come up with a model of a relationship where there aren't discrete people. You could say that there are no terms here that are just based on a single unit, and you
Mhm.
could say somehow a relationship is a completely synchronistic thing in which you can't separate the units.
Mhm.
But here they've chosen a model in which there is such a thing as an intrinsic person without their partner, and being in a relationship is some perturbation to your natural state.
I think yeah, I agree. I think there's a lot of fascinating depth in here. The other thing, when you were talking about multiple oscillators, because in my informational interview, I've been talking to a lot of people who practice polyamory, and so that's also interesting, like how you would then put in multiple people and try to couple them together, and then each person you add on has a different sort of coupling coefficient and stuff like that. Um, so the complexity can increase pretty rapidly. But there are all sorts of interesting ideas here. Um,
Yeah, I mean, the whole multiple, that was actually one of the first things that I thought of when I
mm,
looked through this, because in the talk, I mean, even though Gottman writes this equation as though A is not equal to B, and R1 is not equal to R2, and IHW is not equal to IWH, um, there are various reasons based on my research, but based on the portraits that he showed, the phase space plots that he showed, it really looks like A is generally equal to B, R1 is similar to R2, and IHW is usually similar to IWH, which means these are roughly identical interacting systems. And there's a whole set of literature about when you have multiple interacting units that are coupled together that are identical to some degree of approximation. And that's fascinating because those results are independent of the model. So I use them for my chemical oscillators, but they should also hold for these equations, because at the end of the day, if we're assuming that people are the same, that's all that matters for these proofs to work, that's quite a remarkable feat of mathematics. But the fascinating part is that for a pair of interacting units, there are two universal predicted patterns. One is that the two systems will be equal to one another. And that would be saying that kind of no matter what's going on, maybe the two partners they're both unhappy, but in that state, they would both be unhappy together, or they're happy together. So, I mean, to me, that's a sort of, maybe that's a successful relationship to some extent, in that people are sort of in it together. But I don't know. But then there's another universal pattern in which there's a certain periodicity, and the partners are oscillating with that periodicity, and they're antiphase one another. So that would be saying each of the partners is going through cycles of happiness and unhappiness with some well-defined period t, but they're always opposite one another. So whenever the partner A is in their happiest, partner B is at their least happy. So I thought that was fascinating, but I guess where I was going with this is, even when you go to just 3 units, the number of states sort of explodes. When you go to 4, it's unbelievably complicated. So I've just been thinking about how, right, I mean, these equations are, I mean, they're being talked about in terms of relationships, but this is just sort of a model of interpersonal relationships and how people's happiness can affect one another. So it makes me, I mean, for example, in a ring of 3, a common state that's in fact been observed in frogs communicating with one another in a ring is where one frog croaks, then another frog croaks, then they croak in this cyclic pattern oscillating around. So that's always, I mean, it makes me wonder, like, you know, in my workplace, right, we sit at desks. Are there waves of happiness going through the office, kind of pulsing around or something? I don't know. It's a very out there idea, but
I think it's a really beautiful and interesting idea, because, like, you know, we are all embedded in society, and in many ways we're connected through the internet. So you could have, for example, you know, like a very angry president that is like saying things very far away, but you hear it, and that immediately affects you and the people around you. And now you have some sort of like global agent that's affecting the system. And so it is vastly complicated how humans and networks interact. And these are the same exact questions, to a certain extent, that neuroscientists look at when you've got neurons that may be connected to each other, that are in a population. How are they firing? How do waves go from one group of neurons or one region of the brain to the other region? And then what kind of patterns or ensembles of firing do different neurons have in groups? And how does that then affect the entire system? And there are all sorts of crazy, like, you know, like, what does anesthesia do, you know, to these communications? And then what, in a way, at this very large level, does that mean about these independent agents? So it's kind of cool to think about, like, if you abstract it and use these equations in other systems, what are the implications, for sure?
yeah. And I mean, I guess with the polyamory relationship idea, right? These theorems show that 3 partners in a ring, which I guess would be kind of saying there's one partner that sees the other 2, but then those 2 don't see one another, would be very different than a ring where they're all coupled to one another. So, I mean, I don't know. Without going through all of those interesting patterns, it's just been sort of a trip to me to think about
It's a
how
good point. You
different
know,
activities of people could generate.
some of the polyamory people that I interviewed, they are called solo polyamory, which means that they sort of live by themselves, and then they will sort of like romantically or non-romantically interact with many different groups. And so this would be the idea that the coupling between the different people is very weak, you know, between all the different partners. And so as a result, you don't, it's sort of like a solo, you know, relationship between each person. The system, oscillations in one part of the system will not necessarily affect another in a very direct way. Whereas if you are living all together and seeing each other day by day, that's a whole different vibe, and the complexity probably explodes way more in that situation. It is cool. I wonder if John Gottman has looked at the poly community and seen where the stable points are
Yeah,
there. That
I
would be,
bet he just doesn't want to measure so many people's pulses at once.
that's true. That's true. It would be difficult to measure.
Up with his normative ideas.
Yeah, that's cool.
I mean,
um,
maybe honestly, at least from a network theoretic perspective, from my work, I mean, the number one way to validate these equations would be to see if they hold for a larger network.
yeah,
Um,
legit.
but
That's fascinating. So that's our recommendation to John Gottman et al. Apply these to a poly community and see if it works. It's interesting because like when I talk to people in the poly community, they do say that some of their ratios are changed because they have to master communication and talking about things like jealousy and other stuff that maybe in a traditional monogamous relationship you may not talk about initially or as openly. So they have like, different ways of talking about it, and it could be that their coefficients are different as a result. Uh, who knows? But a deep and interesting thing to look at. Um, so the other thoughts I had was like you have this map over here, and the question is, well, how does this map change? Because this looks like it's pretty set. Like if you have a husband-wife duo, this is their attractor system. But one question that's really interesting is how do these attractor points change maybe if you go through therapy or you go through other different methods. And what really fascinates me also about the movement of these attractor states is that it has a relationship to the research that I do. So I'm just gonna, Ian has already seen this, so this will bore him, but I'll quickly share this. And for anyone that's interested, I have maybe I'll put it in the link or put a link in the description of the video because I have a longer talk that actually explains this a lot better. But what I do is I strap people into a machine like this, and then they're just trying to balance and they're trying to oscillate. And if you look at the time course data here, the black line is just the position, and the green line is the 0 degree point that they're trying to oscillate around. You can see that this person over time has learned to do a great job, and they're just oscillating very gently to the left and to the right. This is a good relationship. And you could see the attractor point, the point that they're always trying to get to is that 0 degree point. They're always trying to get to this point over here. But then what I do is I strap people into the machine and I put them in a condition where they get very confused about where they are. And the data I get is crazy stuff like this, where they begin to drift away further and further and further until they crash. The system crashes. They hit a boundary, and they've lost control. And so what I can do is I can make like these phase plots. This is a position velocity phase point plot where positions on the x-axis, velocity on the y. I'm not going to go through all of like what the meaning is because I've done that in a different talk. I just want to showcase that for this one where people know where they are, it's like there's an attractor point at the center, which is the gravitational vertical. And you're always trying to homeostatically bring yourself to this point. But then when they get confused, it's like that set point shatters and it gets spread across the x-axis. And now they don't know where they are and they're oscillating completely far away from what the right point is. And I guess what I'm bringing up here is what would be interesting is like, are there situations where maybe you start off, in a stable, happy marriage, and then something happens and then it causes the system to crash? You get multiple attractor points that nucleate throughout the phase space, because this is kind of interesting too, that you have very clear one attractor points, which I was a little bit surprised with, as opposed to maybe multiple that are sort of like coming up in space. And the final thought is that, I did like a post previously looking at depression and addiction, and the idea of how addiction also, as time goes by, changes that attractor point. So you start off maybe at a stable, happy place, or maybe not, maybe that's the reason why you're taking drugs and stuff, but over time, it pushes you further and further away, and now you need those drugs just to be able to stay where you are. So these are all examples. Maybe this is confusing what I'm saying, but like the overall thing I'm trying to say is it'd be interesting to see the migration and movement of these attractor points over time. Would be something I'd be interested in looking at. Cool. Any final thoughts, Ian? Or this was a really great sort of exploratory talk.
Uh, yeah, just having a quick think about it. Um, no, I think I've said most of what I want to
Yeah.
say. I mean, I'm definitely very interested. I think we're at an exciting time in history where we can gather this sort of data, like the type of data that you're gathering in your sort of model experiments, which I think are a lot more well defined than love, but
Mhm.
are complex because they involve people and learning. Um, but I mean, it's clear, right, that there has been a lot of successes in sort of quantitative social dynamics modeling. I mean, for better or for worse, like companies like Cambridge Analytica have definitely exploited these sort of ideas pretty successfully. So I think it's worth looking into these. I mean, and taking these more data-driven approaches, but yeah,
Yeah.
and yeah, but I guess at the same time, I caution people against sort of quick conclusions. I
Mhm.
mean, what I'd seen in the talk at least wasn't quite enough to really convince me. Um, but
It's a short talk too. So I mean, I think the concluding idea is that's really cool mathematics. It's a cool application of it. There are interesting ideas there to look at, like thinking about whereas he talks about like this 5-in-1 rule where like you need to be a ratio, like you need to be much more happy than sad. A balanced state doesn't work as well. There's some cool ideas in the talk for sure. The mathematics is really interesting. Using dynamical systems analysis attractor states to look at these things is cool. And then at some point, Ian and I are going to actually look at and read the papers and go from this initial reaction to like maybe a more legit thought process. But yeah, thank you so much like for taking the time out, and I'll come
no
watch
problem.
your
Thank you.
defense. I'm looking forward to it, and sweet.
Yeah, thanks. Thanks for saying this.